Firstly, a quick introduction about me. I'm almost 30, but very important, it's 29. I wrote my first C++ program at the age of 8, but obviously I didn't do that on my own. That was with the help of my dad, but I can claim that I have 20 years of experience in C++, which is nice. The first program that I wrote was with Borland Builder 5 or 6. I don't really remember which one. You don't have to worry about that. It's ancient. I primarily work as a freelance developer, and I'm based in Berlin, Germany. So if you need help with your next DSP audio application, feel free to contact me. So the motivation for this talk, I think we all have our reasons to care about convolution. It's, if you think about the typical workflow in audio production, in game development, in virtual reality, it's used everywhere. So we care a lot about making it more efficient, making it faster so we can use it more, because it's very compute heavy. And there is not really a way around it, because both parts of convolution, both FFT and the complex multiplication itself, are fairly compute heavy. And obviously, very focused on this conference, we have real-time constraints which apply to audio effects, gaming, and virtual reality, as I just said. So, what is the state of the art of current convolution? We do frequency domain multiplication, and we have partitioned algorithms. Just a quick show of hands, who has heard of uniform and non-uniform partitioned convolution? Okay, that's like a quarter, a third, maybe a couple of hands. If you haven't, there is a PhD thesis by Frank Wefers. It's published in 2015, but it's still very relevant today, that goes into all of the details and the typical algorithms that are used. Everything we're going to cover today, if it's typical or traditional convolution or perceptual convolution, they all are an extension to what Frank mentioned in his PhD thesis. So everything you can read there applies to what I'm talking today. It's just what I'm doing is an extension of that. So let's look at the dense convolution case, or the exact convolution. That's what we would typically talk about. We would just say convolution, but we have to give it a little bit more detail now, because we'll have other types of convolutions as well. As it says, it uses a dense matrix or vector for both the filter and the signal. So it depends on if you have a partitioned or if it's not partitioned. You would have, in the non-partitioned case, you would have a dense vector on both sides for both the signal and the filter. And if it's partitioned, you have a matrix, and you would multiply both individual rows of both matrices together to get the result. So, how do we make traditional convolution fast? We have SIMD on basically every desktop platform, mobile platform that exists. Some embedded platforms have it as well, but not really in the sense that we talk about SIMD in the traditional sense, as it is in x86 or ARM. Some microcontrollers have SIMD for fixed point arithmetic. So that would be, you can do in a 32-bit register, you could do 2 16-bit fixed point arithmetic. And then obviously what we can do on desktop systems is, especially with newer hardware, we have the choice of 3 different floating point types. Traditionally in audio, we only use float 32. Float 64 is more academic, and if you do simulations, you sometimes need the extra precision. And obviously, if you can get away with less precision, then that's awesome, because float 16, especially on this MacBook here, runs a lot faster than twice as fast than float 32 if you need to multiply or add or do any arithmetic operations. And I can show you a quick demo of that even with the traditional dense multiplication, you have very different characteristics in performance. So what you see here on the right is just the bunch of different convolution engines. The first one you probably all have seen or worked with. It's just juice DSP convolution. And then I have added a bunch of my own. So UPOS, that's uniform partitioned overlap save. Then you have uniform partitioned overlap add. A second version of that, which I don't actually remember right now what the difference was. I think it's if I used intrinsics or the XSIMD library. And then we have split versions of both of those. Those are, the split is concerned about the complex memory layout. Usually if you have standard complex, you have in memory the real and the imaginary part right next to each other. In split, you have two arrays, one containing all of the real and one containing all of the imaginary parts. That gives us a lot of benefits when writing the code because suddenly using SIMD intrinsics is a lot easier because you don't have to shuffle around the independent real and imaginary parts inside of a SIMD register. So if we just take those, 5 or 6 convolution engines, we take a fairly long impulse response, we select a fairly long signal, which is 10 minutes long, and then we render those. We can see on the bottom here, I probably have to read it out, it's a little bit hard to see, that juice convolution took 3.5 seconds. My engines take roughly 1.5 to 2 seconds. And you can see that the split versions of those run even faster. And I think that's because the compiler is able to do more optimizations. And especially this one, those benchmarks are compiled with fastmath. So I think the compiler is able to do a lot more optimizations in this case. So now you see down here, we have the 6 different engines, and there's already quite a difference in how they perform on this machine. And the results are fairly similar if you go to a x86 Linux or a Windows machine, and they're fairly identical if you go to like a Raspberry Pi, so a low-powered ARM chip. So that's what we have currently if you want to do dense convolution. Those are our options right now. So, yeah, as I just said, we have interleaved and split complex, which is different. So it's a different mindset to program with, but once you wrap your head around it, it's actually all of the algorithms become fairly trivial to implement in SIMD. So now, one step further, which is the one step ahead of perceptual convolution. We'll talk about sparse. Sparse is fairly similar to the dense, except that we don't have a dense matrix or dense vector, but we have a sparse matrix or a sparse vector, which only contains the necessary coefficients, and we'll talk about what that means in a second. So the hopes of using sparse data structures are obviously memory savings if we don't have to store all of the coefficients that we need to multiply the filter and the signal. But it becomes a little bit more complicated because sparse data structures have their own uniqueness, and that's SIMD is suddenly not as easy to implement as it was before because you don't have contiguous or logically consecutive elements are not logically stored contiguously in memory. You might have gaps, and 2 adjacent items may not be logically adjacent in the algorithm. And the same goes for split complex. If you do that with a sparse vector or a sparse matrix, that becomes fairly complex as well, especially because we don't have any pre-made data structures that give us a split representation in a sparse manner. So let's check. I don't know who has worked with sparse data structures before in math. It's a quick show of hands. Okay, that's just a few people. And this one is called compressed sparse row or compressed sparse column. Depends on if you're column major or row major. Because we're in C++, I'm always going to talk about the row version of it, but it's exactly the same if you do column major. It's just that now you flip the row and the column indices in the data structure. So let's go through all of the three data members that we have here. The first one, the values, that's obviously all of the values we actually explicitly want to store, even if they might be zero, only if they're not zero in this case, in the sparse case. And then we have the column indices and the row indices. And the column indices just tell us the value we got from the first one, what is the logical position in the matrix. And the row indices tell us at what point in the array does the new row start. So we can calculate a two-dimensional index with those two. So, as I said, memory savings. This is for the compressed sparse row or compressed sparse column, it doesn't really matter. So on the x-axis, you have how many values you actually want to store in the data structure, and on the y-axis is how much memory have we actually saved. So you see the break-even point for both 32-bit and 64-bit integers is around 50 to 60%. Above that, it doesn't make any sense to use a sparse data structure, and if we store less than 50% of the values, we get huge savings fairly quickly. So now the question becomes, how does that relate to performance? And we can go back to the little demo program that I have, and we will just, because we have too much stuff here, we'll just select one of the dense convolvers and one of the sparse convolvers, and we can run the benchmark, and we'll quickly see that it takes a while. That's always not a good sign. It's 3 times, 4 times slower than the dense case, so not really a great start. But as I just said, sparse only makes sense if we actually have a sparse data set and don't want to store all of the values. So I have this slider up here on the top right where we can analyze the impulse response, and then we can just say, actually, we don't care about any coefficients that are below a certain value. So now when you see, when I slide this down, everything that's turning white are coefficients that we're going to delete. So let me quickly explain the top graph. It's on the x-axis, you have time, and on the y-axis, you have frequency. And in this image, you have all of the partitions that make up the convolution. So now when I have this slider at around, 60 dB, we can see on the bottom left right here that we actually only keep 37% of the coefficients that we wanted to have, or that were there originally. So now the question becomes, does this run faster? Like, I've just arbitrarily picked the 60 dB dynamic range. We have 37% of our coefficients. Is it faster than the dense case? So we have 1.7 seconds for the dense case, and now we have 1.6 seconds for the sparse case. So now we have a break-even point. They're roughly the same speed. So what happens if we actually go a lot slower, take a lot less coefficients? So now we have a dynamic range of 25 dB, so horrible, but we also only need to use 6% of our coefficients. So how fast does this render? We have again 1.7 seconds for the dense case, and for the sparse case, we have exactly 1 second. So that sounds pretty good. But as you can probably already imagine, if you listen to the result of that, it's going to suck fairly badly. You're going to have artifacts. It sounds like the rendering glitched. It's not what you want. So now the question becomes, how far can we push it that we as humans actually don't hear a difference, or the difference is okay? So if we don't have a context around it, people think, oh yeah, that's the original impulse response. We don't have to, it sounds fine. So that's where we go from sparse convolution to perceptual convolution. And the whole key about perceptual convolution is how do we sparsify the filter so we only have those coefficients in the filter that actually are important. And as you could already see by the image that I showed before, we can show here that if I move the slider, the first thing it does, it removes all of the high frequencies, and the more we go sparse, it eats into the low frequencies as well. So how can we use this to our advantage? What I've showed you in the last couple of minutes is that I had the simple threshold function that just is this bin of after we converted the impulse response into the frequency domain. We look at all of the individual frequency bins. We take the energy of that or just the amplitude. Is it above a certain threshold? That was just the naive case that I showed you before. We can also do different frequency weighting functions. So you could think about, we have A weighting, C weighting, different weighting functions. You could even think of your own. We can apply those, and then we select which coefficients are still above the threshold or something else. And then you can always do a hybrid, which I'll get back to in a second. So the naive one, coefficient selections that I just talked to you about just a second ago. We converted the filter to frequency domain, we converted to dB, and then we just ask the simple questions, is the coefficient above the threshold or is it not? And then we pick the ones that where the answer was yes, and we put that into our sparse data structure. The weighting coefficient selection is almost identical, except after converting to dB, we apply a frequency weighting function. This could be any of the common ones or one that you selected yourself. And then we ask this exactly the same question, is the coefficient above the threshold or is it not? And then one that's a little bit more advanced, but not really that much, is that you can do this to the naive case or the frequency weighting case, is that you have a dither section, which is right above or in front of the threshold. Dither could also be just replaced by random. So if all of them fall exactly onto one like dynamic range, you can always randomly pick, okay, now we pick this one, now we don't. Maybe that improves the quality. So I can show you an example of this as well. On what we didn't talk to you, what I didn't talk to you about yet is the bottom image. So the one you see on here, and that's a histogram of the distribution of the filter in which bin the dynamic range of all of the coefficients fit in. And the red bars are just minus 32 dB, minus 64, and minus 96. And you can see with this impulse response that there is this weird below 64, this weird thing where almost all of the bins for this filter are exactly at, I think it's around 70-something dB. And the question now becomes, okay, why is that? And I'm pretty sure that that's because this impulse response was from a hardware device that was running 12-bit. So that's exactly the limit of the filter that we have. And I can show you another example. Let's pick another one. This one, it has exactly the same, that it's all stored, that the limit for this one is at like minus 70 something, which is the 12 bit depth. So now I have another option here on the right, which has a weighting function. I just implemented one simple one just for visualization. Like disclaimer, A weighting is not the best one to use for audible stuff, but at least we can pretty visualize what's happening here. And now you notice that there's one constant bin where all of the low amplitudes were exactly at one bin, it's now blurred across multiple bins. So now if we can see this one, I think I had it with the, if we don't use a filter, there is this case at 72 dB where we keep all of them, and as soon as we go down just 0.1 dB, suddenly it's like removing 70% of all of our coefficients. If we do the same with A weighting, it suddenly looks a lot different, but we still have roughly 30-something% of our coefficients that we are actually keeping. And then the rendering performance should stay exactly similar as with the non-weighted case, because it's not dependent on which coefficients you take, but just how many. So now you noticed, okay, we are keeping too many. It's slower actually, but what happens if we again go down a little bit? So let's say 59 dB, we're only keeping 20% of our coefficients. And then we see the same again, that the dense case took 5 seconds to render the 10-minute audio, and the sparse filter took only 3.4 seconds. So that's, what is that? That's a 30% improvement roughly. So that's cool. So, but we probably want to go a little bit more into the depths of how is that actually implemented. Because it's all, like you just saw, I think I don't have to tell anyone that that is a JUICE application. So it's written in C++, but C++ lacks abstractions for sparse vector and matrix types. At least C++23 gives that std_md span, which is a dense vector or matrix, but we can also use that to implement our own sparse vector or matrix. C++26 will give us std linear algebra, which is essentially a pretty interface over the BLAS libraries, which I had to implement it on my own because there's only one reference implementation. So, but yeah, once we get that in C++26, we'll have lots of algorithms that are fairly nice to use in DSP in general, but especially when it comes to anything with convolution, frequency domain, lots of data structures, lots of multiplication. So, but what if we want to apply this technique to any existing convolutions engines, which I call dense again, you probably just call them convolution engines. So how much effort would it be to apply all of these techniques to JUICE convolution? Well, basically, because we're modifying the filter after it has been converted to the frequency domain, which is an implementation detail in the JUICE convolution engine, we would have to fork it, modify it, and add hooks so we can get the filter after it has been transformed to the frequency domain, remove all the coefficients that we don't care about, and then the convolution engine has to pack that into a sparse data structure, and from there on it's almost identical to the dense case. I've actually tried to implement this. I got sidetracked with a couple of side projects, as we will see when you look at this GitHub repo. So this is not only a convolution library, it's also a general purpose DSP library for C++. And then, as I said, I got sidetracked. I also wanted to, in the spirit of std_md span and std linear algebra, I wanted to see what it would look like to have a std FFT library. So you can also see my attempts to implement that there. But yeah, that GitHub repo has library code and this simple demo application, which, disclaimer, is only the uniform partitioned algorithm mentioned in the PhD thesis by Frank Wefer. It's not yet non-uniform, and the real-time, it's actually a plugin, but the real-time processing is broken, so you have to use it offline currently. So, yeah, and the like the whole theme for my library was I wanted to write it in a way that would be close to as if it were implemented in the standard library. So that's the standard abstractions there. That was the main part why I got sidetracked into FFT, because almost every FFT library is C-based and a pain to work with, even though they're really fast. But I tried to, and I think successfully, for the one-dimensional case, added an abstraction layer that's suitable for modern C++. So I've already given you a quick demo, but we can just look at one more really long impulse response. This is it's over 260,000 samples. So that's what is it? Is that how many seconds is that? 265. So that's a 6-second impulse response. We have a 10-minute audio clip. And you can see here that when we do a dynamic range of 60% of 60 dB, we're only using 10% of all of the coefficients that we would have used in the dense case. So we can see what this does to performance. And you can see that, okay, it runs a little bit faster, but not that much. And again, if we go down, so we have 40 dB of dynamic range. And we can see it's, again, 2 seconds for the dense case and 1.2 for the sparse case. There is a point where going even more sparse doesn't really make sense, both in computational aspects and in, obviously, audible aspects. Now we only use 0.7% of all of our coefficients. And if we render that, we still have the 2 seconds for the dense case, and the sparse case didn't get that much more faster than it already did with the 40 dB dynamic range. And the reason for this is that even though we're using a lot less coefficients, so we have a lot less complex multiplications, we still have the constant overhead of an FFT and an inverse FFT, which both in the dense and the sparse case will always be present. So let's go to, and the repo also has a simple CLI application where you can test all of the engines. You'd have to give it an impulse response and a signal file. It currently is limited because I wanted to implement the CLI application without juice. It's one of the limitations is you have to use an impulse response and a signal that have the same sampler rate, because I don't have a resampler yet in that application. So the question now becomes, how can we, like I've always just manually pulled the slider down and they're like, okay, let's pick 60 dB dynamic range, let's take 50, but how much dynamic range do we actually need? And I labeled this the automatic sparsification problem. Essentially what I would like to have is a function that you give it the impulse response and it tells you, okay, if you only use 60% or 60% of all the coefficients, you get a quality score. But that I haven't solved this problem yet, so that's actually fairly difficult, because if you think about how you would normally test DSP algorithms, if you have like a golden truth, that's how it's supposed to sound like, and you take the sparse convolution and you're trying to compare those, usually what you do is you would do like an absolute error or like a relative error measurement. But as soon as you leave off frequencies in the whole computation, those fall apart. They will give you, okay, yeah, those signals, they don't look anything alike, but they might sound alike. But so it's for the computer, it's difficult to say how much quality have we actually lost. One of the, talking to ChatGPT a while, one of the ideas that it came up with was maybe you want to do the wavelet transform to analyze the IR, which is similar to what some compression algorithms do. I don't know, most people probably haven't worked with wavelet transforms yet. It's in spirit similar to an FFT, but the output of a wavelength transform are detailed coefficients and I don't know what the other ones are called. Essentially, the wavelet transform splits your signal into what's the detailed part of your signal and what's your main part of the signal. So this sounds promising, but the issue is that the point in the chain where we actually delete the coefficients that we don't want, we already have the IR in the frequency domain. And the wavelet transform doesn't convert the signal to a frequency domain. It's a completely different thing. So the matching up of, it would be a two-step process. You would first have to take the impulse response, convert it with the wavelength transform, analyze it, have some sort of representation. Okay, we can delete this much of the high frequencies, this much of whatever, but it's fairly involved. So I haven't figured out how to do this properly yet. If you have any suggestions on it, how we can perceptually, so essentially what we want is we want a metric to see how perceived equivalent are two audio signals, and not how accurate they are mathematically, but how are they perceived by humans. And I think that's a general issue in anything DSP related, is the perception of humans, especially because if you give it to some people who are not daily involved with audio, they might perceive it totally different to someone who's working in a recording studio the whole day. So let's quickly summarize the different kinds of convolutions that we talked about. The dense case that all of you already know about is the multiplication of the signal and the filter in the frequency domain using dense data structures. So we use all of the coefficients, all of the signal, and all of the filter. Then we have sparse convolution, which is the multiplication of the signal and filter, again in the frequency domain, but using sparse data structures, so not using all of the coefficients. And a specialization of this is perceptual convolutions, where we use metrics of human sound perceptions in the sparsification process. So yeah, we need some sort of more advanced algorithm that tells us how we can reduce our filter. So I think I'm already done. I just want to mention one thing quickly, is that I always talked about making the filter sparse and not making the signal sparse, because in convolution you both have the filter side and the signal side. And because I work in a context where like almost everything I do is real-time based, so I briefly thought about, okay, can we make the signal sparse as well? But that actually brought in a huge problem that it would be a non-constant CPU load. So depending on how loud, how the frequency distribution in the input signal is, you would have CPU spikes. So just imagine that you have multiple drum channels, and then every time the drummer hits the bass drum, suddenly you have a CPU spike, which would kind of suck. So, it's not deterministic. So I haven't played around with that anymore, but maybe it makes sense for some use cases. Yeah, thank you. That's it from my side.